You're not going to want to miss this episode of the AI show where Andreas shows us how to do audio, but he kind of makes it like vision in a cool platform. Make sure you tune in. Hello and welcome to this episode of the AI show where we've got a special guest, Andreas Vrålstad, to talk about deep learning with audio. We don't get to talk about audio much. I'm pretty excited. So tell us who you are and what you do, my friend.
Thank you, Seth. I'm happy to be here. So I work at a company called Peltarion here in Stockholm, and we build an online platform where you can build and train your deep learning models and deploy them so you can use them in your own processes or applications afterwards. So you can do things like classifying images or do sentiment analysis on text, or you can, as we're going to look at in this episode, we can classify audio as well and work with that. So I'll just start diving into that to show you what we are going to do here today, which is training a model to recognize moods in music. So I will dive in real quick here and just show an example of what we're going to do.
Let's do it.
So we are going to go back to this code later and dig into it a bit deeper. But right now, I just want to show you what we're going to do. So first thing we do is we will load a song, and let's listen to that because we want to detect the moods in it, right? So I'm going to play it for you now. So let's listen to this.
So that feels like a happy song, right? Or hopeful?
Yeah, I would say hopeful for sure. And so let's see what the code think about this. Yeah, it feels like it's detected the same kind of moods as you, Seth. They found hopeful, happy, running, and restless. And yeah, those are the main ones. So let's jump out to how to build and train this model.
Let's do it.
So when you log into the Peltarion platform, this is the first thing that you see. So you have your dashboard here where you can see your projects on the left side. You can see that I created quite a few, work on the platform for a while. But what we want to do here is to start up a new project for mood detection, which is what we're going to do today. And since we have some files to upload, I created it already. You can see it's 1.8 gigabytes of files. I don't want us to sit here and wait while I upload the files. But let me explain what the platform is like here. So we have essentially 4 different views. So first one is datasets. We work with getting data up on the platform. And then we have modeling, where you model and or build and train your model. And then we have an evaluation view where we can look at the performance of the model. And if you're happy with that, you can proceed to the deployment view, where you can deploy the model and make it accessible through a REST API. So now I'll just go through the different views here and you can see what you can do. So starting with the dataset view, there's some different ways to get data up on the platform. One is to upload a dataset from your computer, or just provide an URL to a zip file, for instance. You can also import data from, for instance, Azure Synapse, and we are working on being able to import data from more places as well. We can also push data to the platform through our data API, and you could also use a free data set from our library. We have like a number of data sets. It's 30, 40 something data sets here that you can use and build cool models on and get started. So, but I uploaded a data set from my computer already. So let's click on that and see what happens. So no matter what data set or source of data you have, this is what your data set view will look like when you have the data on the platform. So you can think of this as a spreadsheet, kind of. You have a number of columns with different data in it, and then you have the rows for each sample. So any of this file, we have the audio file as a spectrogram. We will get into that a bit later for those of you that haven't worked with that before. And we have all the different moods here as well. And it's binary coded, so it's a 0 if it's not present in the audio file, and there's a 1 if it is present, according to the one that's tagged all these files. So we can see we have dreamy music in here, or the tag. It can be epic, it can be funny, and it can also be casino, whatever that is. And this is what we have. So to get started to work with this data set, we want to have in the model, we want to have build our features together. So we have one input, and the spectrogram is going to be the input, right? Or they think of it as an audio file for now, and then you want it to classify it as any of these, or tag it with these tags here. So to do that, we create a feature set. So we see the list of all the inputs here. So select all of them and remove the ones we're not going to use. For instance, we're not going to use the inputs, and we can call this one moods or something else, but I think moods is a good name here. So now we have moods, and now there's nothing more we need to do here, so we can save a version. And save version here is like version handling, so we can build a model and train it, and we can go back and train it again with, maybe we want to do some modifications with our data set. Maybe we want to try out normalization and see if it performs better. So then you just go back here, make that change, and you get a new version. But now we're gonna try it with this one. So just press use a new experiment. And when you build a new experiment, you can use one of the snippets that we have on the platform already, or you can build everything from scratch, which is, you might want to do that to try it out, but usually you are better off using one of the datasets on the platform. So when we press the button use a new experiment, this wizard pops up, and we want to select the input, which is the spectrogram, or the audio file in this case. And then the output is mood. So we want to send in a spectrogram, and we're going to want to get out all the moods detected in that one. So then we press next, and then we can select what kind of problem we have here. In this case, it's a multi-label image classification. So meaning we're going to put in an image, and we want to have multiple labels out. So let's select that one. And I also need to come up with a good name here. So our experiment, it's anything really that makes it possible to find experiment later. And you see when we selected this problem type, a number of different models pops up. We can try multiple of these, but for now we're just going to use this one, DenseNet 169, which I found out works quite well with this dataset. Now press create, and now we got to the modeling page, and we can see here is the canvas with our deep learning model. It looks quite small now, but we can, if we want to start to expand the different blocks, and we can dig deeper into it, and we can see that there are many layers to it, and many things in it. So this is what we get here. We could also build this from scratch if we want to, using snippets and also different blocks that we have here. Yeah, it's here already. But we're not going to do that for now.
So can I ask a couple questions as this is running? So basically, you're using transfer learning with a DenseNet 169, and you're literally just putting it directly in and saying run it through that. But you could, in theory, stack any number of different neural network architectures together to build anything with this kind of approach. Is that would
Yeah,
that be fair to say?
yeah, absolutely. That's correct. So all you need to do that is go back here to snippets and find the ones you want, and you can add them to the canvas like this, and you can just connect them together by adding connections like this. So that's possible, absolutely. So you can make any combination that you want here.
And does it figure out, and here's the part, like I always make these dumb errors when I'm like building my own convolutional neural networks, like the input shape to the blocks,
Yeah,
it has to be like, height by width by channel, for example, with images.
yeah,
Does it automatically calculate those connections for you so I won't get that wrong?
it does. It does. So get it
That's cool.
automatically. Yeah.
And so basically what you're doing here is you're building the whole neural network structure, and then you're just running data through it. Would that be about right?
That is correct. That is correct.
And how long does it take to build these kinds of things?
You mean training it from where we are now?
Yeah, training. Yes, yes, sir.
So that will depend a lot on, especially on how much data we have. So this data set is roughly 1.8 gigabytes, and also the model and how big that one is. So now it's like there are some different denseness. Now I selected one that is quite big, or it's not the smallest one, so it will take a bit longer. So, but for small data sets with simple models, it can take, say, half an hour maybe, train something that you can actually use. And this one takes, try this before, and it takes roughly 5 hours. So it takes a while. So you can, of course, you can also select your number of epochs and stuff like that to make it, run, or like for a shorter time, but with lower performance in that case.
Mm-hmm.
But what it can do is just turn up the number of epochs and use early stopping, and it will quick stop as soon as the result isn't getting any better.
And what's cool is that I'm looking at the optimizer. You can literally choose the optimizer and change the hyperparameters to the optimizer in there as well. Looks like, because the beta one, the is that a beta? Is that a little beta? I think that's what that is. But there's two parameters. There's two parameters to the optimizer, beta 1 and beta 2, for specific to Atom, the Atom optimizer. And if you're using like LMS prop or SGD, those parameters would show up there for you to change as well, right?
Yeah, correct. And depending on the model, we put in some default values that often works quite well. But here you can do some tuning as well to try something out and tweak the performance, make it perform even better.
That's awesome.
So when we're happy with the model, and now we've been talking on this view for a while, but we haven't actually done anything about it. We're just using the default model. Then we press run here in the upper right corner. So, and now it's starting training. So, and now it will run for 5 hours. So just go grab a coffee and see you soon. Now we actually prepared a model already, so we can just go to the next step here with a train model. So let's do that. I'm going to go back here to projects and have a look. So now going into another project it's the same model, and we trained it already. So that was the wrong one. It's here, experiment 1. So we can see it's the same model, and it's done training. So let's see. Then we can go to evaluation view, and we can have a look here. And here you can go through some different metrics to see how it performed. Also getting some information on what it is. You can also you can see the curve here as well on how it went during training. Yeah, so we can go to the predictions inspection here, and we can have a look at the confusion matrix. So we'll just spend some time to load, and here we get it now. So we can try modifying the threshold and see how it performs depending on that. So we see something around here. It performs quite well.
That's cool.
Yeah, and when we're happy with this one, we can go to deployment view. And what we need to do now is just press new deployment. We select our experiment and the checkpoint that we want to deploy, and press create. And then enable. And what happened now is, using the credentials here on the right side, we can call this model. So just calling this API with these credentials, sending in a spectrogram, and we can get out the features that we can see in the list here. So yeah, so that's all we do on the platform.
That's pretty amazing. So basically, you went from data to modeling using drag and drop, which was actually really cool. Drag and drop modeling. Then you took the training, you looked at the experiments, and then you deployed the best model depending on the whatever metric you chose, and that's how you went about doing that stuff. Is that right?
That is correct. That is correct. Exactly. So yeah. So I'm just trying to make it as simple as possible, working with this graphical user interface and deploying it. So I'm thinking, we were talking a little bit about spectrograms earlier, and so maybe confused. We were classifying or tagging audio, right? But talking about spectrograms. So what about digging into that?
Yeah, and that's what I was going to ask you. Like when we're looking at these, like I'm on your screen again. I saw that you actually did an image classification and not an audio classification. Can you explain what that's all about?
Absolutely, absolutely. I'm thinking about I made a presentation here so we can have a little look about spectrograms as well, to explain the background and see how it works and why I'm using image classification. I think it will make a bit more sense after the presentation.
Let's do it.
So let's have a look at that. So just a reminder here, what we want to achieve is going from an audio file or some music, and we want to get the moods out of that, if it's a happy song or a sad song or whatever. So, and you can do that using you can actually use the raw audio file if you want to, and the samples, but usually we get much better performance if we first translate that audio file into something called a spectrogram, which is in turn can be interpreted as an image that we can use as input to our model. So let's have a look at what a spectrogram is. In one way, you can think of it as seeing sound. So here's a quick picture. We have the waveform on the left side, and we have the spectrogram on the right side. So in the spectrogram, you have the time axis like horizontally, just like in the wave file on the left side of the screen. But on the vertical axis, we have frequencies. So and the color of it on this image is purple and black. There's no reason for that, but the intensity for each pixel will say how much there is of that frequency in each time sample. So let's have a listen to a few of them. So there are 3 different spectrograms here. So let's listen to them and see if it makes more sense. So we're going to start with the one on the left side. Let's listen to that. Yeah, we can kind of hear when the beat is coming and see how that fits into the image. So let's have another look at the one in the top right corner. It looks like it's going up a little bit. So let's listen to it.
Yep.
Yeah. And Seth, what do you think about the one in the bottom right corner?
Oh, you're putting me on the spot here, but it looks like it's all over the place. So I'm going to say it's like and it's at the bottom too. So how about something like that?
Nice. Let's listen and see. That's great. Yes. That's great. That's exactly what it is. Just a lot of noise everywhere. So really cool that you could see that one. So you only needed like 2 samples for training yourself to understand what the third one is. That's great.
I am smarter than a neural network sometimes.
Exactly, a lot actually. So really cool. So, but I hope these images helped you understand a little bit what it is. So let's dig into how to create these spectrograms as well. So it's actually, I would say it's quite easy. So you start with taking a small slice of the audio file, and now we can just zoom in on that. You just take a few samples. Usually an audio file is maybe around 20 or 44 kilohertz, depending on your application. And so you have a lot of samples in time, right? But this is zoomed in, and now we use Fourier transform based on these audio samples. And then from this small sample of audio, we create the first part of our spectrogram as well. So, but instead of just seeing that what you see there, we can actually see the frequencies in a sense.
Interesting. So basically, if I'm understanding this right, you are basically taking like an audio file. You're doing a Fourier transformation, which basically separates it into its respective frequencies and intensities, and you're making that an image, and then you're doing image classification on it. Is that what am I understanding that right?
That is exactly what we're doing here. That is correct.
I see. And that's why I was confused, right? Because you're doing image classification on audio. I'm like, wait, this doesn't feel right. But now that you're explaining this makes a whole lot more sense.
Great. I'm happy to hear that. So that makes more sense now. So so this is what we're doing, and the reason, as I said, is just that it happens to be often we get much better performance doing that. So pre-processing using the Fourier transform. So that's what it is, and then we just do this for the whole wave file, and then we have our spectrogram.
Well, this is awesome. And so my question to you is like, how do you load this up and convert to a spectrogram? Is that happening in the platform automatically? Is there a way that you can do that in code as well?
We're doing it outside the platform, so doing the more advanced pre-processing, we do outside the platform to build that. And in this particular case, we use a library for that in Python called librosa, which is very convenient to work with to transform raw audio files into spectrograms, or MEL spectrogram, which we actually use here. So essentially, it's just one line of code, like we see on the screen here. So it's amazing to work with it. There are other libraries as well, but I find this very convenient to work with. So let's dig into to the code as well. Yeah, just what we're doing here is we take the spectrograms and we put it into the model as we saw, and we get out the tags, right? So that is all we're doing. So are we up for having a look at the code?
Yeah, let's do it.
So we saw this one real quick earlier, but just let's have a look at it again in a bit more detail. So we start out with loading dependencies, of course, and the one that I want to talk about here is librosa, which we're using to convert the audio file to MEL spectrograms. And we have one library called Sidekick as well, that you probably haven't heard of because it's a Peltarion developed library, which is just the Python bindings to work with the deployed API. So let's run this one. And next step, we load the song and the one we listened to earlier. And what we do here is we just use 30 seconds of the song. So we don't use the whole one for performance reasons. And usually you don't need more than 30 seconds. I think in the start of this episode, we'll listen to the song for like 20 seconds. And Seth could still hear that it was like a happy song. You can feel that quite quick after. Of course, there are some songs where it's more tricky, but usually that works. Now we loaded the song. We can use this MEL spectrogram line, which is like doing most of the magic here. So let's run that one and have a look. And what we want to do based on this is to run it and turn it into grayscale as well, which is what the platform expects as an input. So this is what it will look like then. And that's it for pre-processing. Now we just send it to the platform. And the URL and token here is just taken from the platform. Let's go back and have a look at that. So just copy the URL and token from here and copy it in, and then we run it. And then we get our predictions based on our image. So sometimes when you just deploy the API, it can take a little while for the first call. So now it's done, and let's look at the moods. Yeah, and here's the output. So all the different moods. So that's it.
Well, this has been really, really cool. I've like I said, I'm very good at computer vision, and so the fact that you've actually made audio into a computer vision adjacent problem has been really cool, and I love looking at the platform. Where can people go to find out more?
I'm happy to hear that, Seth. So a good starting point is have a web page, and what you could do is I suggest is going in and creating an account. It's free, so you can go in on the platform, just create an account, try out some of the data sets that you have on the platform, or if you have a data set on your own, and and have a look at the webpage and just let me know if there's any questions.
Well, thank you so much. This has been really amazing. And thank you so much for watching. We've been learning all about tagging audio using deep learning with a cool platform called Peltarion. Thank you so much for watching, and hopefully we'll see you next time. Take care.